So now we're going to look at the common ion effect as it relates to the solubility of sparingly soluble ionic compounds such as silver chloride and so on. Now, remember what the solubility effect is all about. We talked about it in relation to weak acids and weak bases. Basically, the presence of a common ion will suppress the dissociation of a weak acid or weak base. And the same is true for ionic compounds that are sparingly soluble like silver chloride, etc., right? So as stated here, the presence of a common ion decreases the solubility of the salt. And as an example, I'm going to work this particular question. What is the molar solubility of silver bromide in pure water and then in 0.0010 m silver bromide? So let me get out of this here and go here and create a new sheet to write on. Okay, so silver chloride, AgCl. Okay, so let me write it here. AgCl solid when added to water. I'm sorry, silver bromide, not silver chloride. AgBr solid when added to water, you're going to get Ag plus aqueous plus Br minus aqueous. All right. And the KSP value for silver bromide is 7.7 times 10 to the minus 13. Okay, so I'm going to set up the ice table here. Now, in pure water, you would have no silver ions and bromide ions to begin with, right? Again, we don't need to worry about this because it's in a solid state. The change here, however, would be that if S is the solubility of silver bromide, in fact, let me put that up here so that we can be reminded of that. S is equal to the solubility of AgBr. All right? So if that's the case, then the change in the concentration of silver would be plus S, and the change in the concentration of bromide would be plus S as well, right? So at equilibrium, you're just going to have S and S here, which means that KSP would be equal to S squared, which means that S would be equal to the square root of KSP, which would be equal to the square root of 7.7 times 10 to the minus 13. And according to my calculations, that would be 7.7 times 10 to the minus 7.7 times 10 to the minus 13. Square root of that, according to my calculations, that would be 8.8 times 10 to the minus 7. So 8.8 times 10 to the minus 7 m. All right, so that's a molar solubility of silver bromide in pure water. All right, now the next part of the question says, what's the molar solubility of silver bromide in 0.0010 sodium bromide? So what that means is that I'm going to make a change here. Let me erase this here. So instead of 0 here, you're going to have 0.0010 m of bromide, all right? So that changes things a bit because now down here, let me erase this here. Down here, as far as the bromide ion is concerned, its concentration at equilibrium is going to be S plus 0.01, I'm sorry, 0.10, all right? So the KSP expression, let me just create a line here so there's no confusion. So the KSP expression for this now would be S times S plus 0.0010. Now at this juncture, we can make an assumption. We can assume that S is so small compared to 0.0010 that this part here effectively becomes 0.0010, right? And that would be equal to the KSP. So therefore, S, based on this, would be equal to KSP divided by 0.0010. So the KSP is equal to, as we said before, 7.7 times 10 to the minus 13 divided by 0.0010. And that works out to be equal to 7.7 times 10 to the minus 10 M. So this would be the solubility of silver bromide, where you have already in the solution this amount of bromide ions. And you'll notice when you compare this value to this value, you see that this value is smaller. And this is a demonstration of the common ion effect, because the common ion, which in this case would be the bromide ion, when present already in the solution, will force the equilibrium in that direction and therefore reduces the solubility. So therefore the solubility drops from 8.8 times 10 to the minus 7 in pure water to 7.7 times 10 to the minus 10 in the solution containing 0.0010 M of bromide ions. Okay, so that's basically how we do a problem of that type. All right, what next? Another thing important that we need to discuss is the effect of pH on the solubility of certain ionic compounds in an aqueous solution. So in some cases, well, let me just say this. So the presence of the common ion decreases the solubility. So that's a common ion effect, right? Insoluble bases will dissolve in acidic solution, and insoluble acids will dissolve in basic solutions. So just to give you an example, magnesium hydroxide, right? Basic compound, very insoluble. And as you can see, when it's added to water, you have that equilibrium taking place. So the KSP value for magnesium hydroxide is 1.2 times 10 to the minus 11, all right? And that's the expression for the KSP. So if you rearrange this to solve for the solubility, you're going to get the solubility be equal to 1.4 times 10 to the minus 4. So I'm quite sure by now you understand the steps that are taking place. S would be the solubility of magnesium hydroxide, which would mean that S would be the concentration of magnesium. 2S would be the concentration of hydroxide. And you plug those values into this equation and you end up with 4S cubed equal to KSP. And then you solve for S, which is 1.4 times 10 to the minus 4. Now, the concentration of the hydroxide ion is what we want to focus on here because it's basic. The concentration of hydroxide ion is equal to 2 times S, which is 2.8 times 10 to the minus 4, all right? So what that means is that for a solution where the magnesium hydroxide is added to water and it achieves equilibrium, the pOH is equal to 3.55, and therefore the pH is equal to 10.45, all right? So this number is what we need to pay attention to, because if the pH of the solution is less than 10.45, right, then that means that the equilibrium will shift. Well, what will happen is that the hydroxide ion will react with any added acid to lower the pH to form water, right? So therefore the concentration of the hydroxide ion will be lower, and therefore the equilibrium will shift to the right, okay? Because you're decreasing the concentration of OH minus, the equilibrium will shift to the right, which means that the solubility of magnesium hydroxide will increase. On the other hand, if the pH is greater than 10.45, then what will happen is that you're increasing the concentration of the OH minus, right? That means that the equilibrium is going to shift to the left, which means that the solubility of the magnesium hydroxide will decrease, all right? So that's basically how the pH would affect basic ionic compounds like magnesium hydroxide. If you lower the pH, it will increase the solubility. If you increase the pH, then you're going to reduce the solubility of these compounds, all right? All right, so that's basically that. So the next video, we'll be talking about complex ion equilibrium and solubility. And then I think after that, I'm going to work a few examples so that, again, you get an idea as to what you can look forward to. Okay, so that's it for now. Until next time.